Hi, I'm Zor. Welcome to Unizor Education. So we will continue talking about Euler-Lagrange equation, and basically we have considered the applicability of this equation to non-Cartesian generalized coordinates, and we will do exactly the same during this lecture, but from a completely different angle. Now, this lecture is part of the course. Course is called Physics Plus. That's for all, and it's presented on Unizor.com. This is the website, totally free. No ads, no sign-in is necessary, no subscription. What's interesting about this website, I mean, you might find this lecture on YouTube or somewhere else, but I do prefer you to use the Unizor.com, not only because it's free, but also, and no advertisement, etc., but also because every lecture is supplemented with detailed notes, like a textbook. And for this lecture, it's very, very important, because I will definitely refer you to this textual part, notes for this lecture. I'm not going to present all these mathematical tricks, whatever is necessary to conduct the material. It's all presented in writing, in the notes, which are presented on the same screen on Unizor.com, where the video lecture is. So I strongly recommend you to have this on a computer and go to Unizor.com and the website. So you go to course Physics Plus for all, and one of the chapters is Lagrangian, and this is the lecture within this chapter. It's called Euler-Lagrange Equation Invariance. Well, I should say covariance, not invariance, but later maybe I will talk about this. All right. So let's get back to business. So let's consider we have certain mechanical system which has certain degrees of freedom, and we have a configuration space where we have defined Cartesian coordinates, which are basically S1, etc., Sn. So n is the number of degrees of freedom. Sometimes I will use just a plain letter S or Si to shorten the notation. At the same time, in the same configuration space, there are generalized coordinates, which I use Q1, Qn, or just letter Q, or with an index. So these are two systems of coordinates in this configuration space, which basically define the state of the system. Obviously, all of them, if we are talking about the moving system, then they're functions of time, obviously, because at any moment of time they define the position of the system. And obviously, the velocity is a derivative of these functions of time by time. Okay. Now, what's interesting is that these are two equivalent, so to speak, systems of coordinates, in a way that one is transformed into another and back. They are one-to-one corresponding, which means that for any Si, there is some kind of function, capital Si, of all Q, and for each Q, there is some kind of a function, Qi, of all S, which are converging systems into another. Equivalent, you can say that, for example, the Cartesian coordinates in the plane can be a function of polar coordinates, something like this. These are conversion transformation function, if you wish, and backwards. They are smooth functions, which means they are differentiable, at least twice. we need it. Now, what's next? Next, I would like to approach the covariance of Euler-Lagrange equation in different systems of coordinates, in Cartesian coordinates and in generalized coordinates. Now, before, in previous lectures, I was actually talking about this invariance or covariance, more exactly, of Euler-Lagrange equation based on action principle. So I kind of proved, well, logically made a good foundation, let's put it this way. The word proof is kind of too strong maybe. But anyway, I logically explain why the Euler-Lagrange equation is the same in Cartesian coordinates and as is in generalized, based on action principle. Now, that's very important, but I would like to approach it differently in this particular lecture, more mathematically. I mean, what does it mean that the Euler-Lagrange equation is as good in generalized coordinates as in Cartesian? Here is what it actually means. First of all, the idea from the very beginning of this particular chapter of the course was that Newton's second law, which is applicable to Cartesian coordinates, is an axiom. We just take it as is. Then I have basically derived Euler-Lagrange equation from Newton's second law in Cartesian systems of coordinates, just based on the fact that the mechanical system we were talking about is conservative, which means that the force is gradient of potential energy, and basically just from this I have derived that Euler-Lagrange equation is basically equivalent to the second Newton's law. But this is Cartesian, because Newton's law is applicable to Cartesian, I mean, without any problems, let's put it this way. Now, and then I needed the action principle to basically explain why Euler-Lagrange equation is good in generalized coordinates. Now, in this case, I would like to derive this without action principle, derive it mathematically. In the same way I derived from Newton's law, I derived Euler-Lagrange equation in Cartesian coordinates, I would like to derive from Euler-Lagrange equation in Cartesian coordinates, I would like to derive from it the same equation in generalized coordinates, without resorting to any kind of action principle, extremals of functional, etc. That I suppose you have to know from the previous lectures. But I'm not going to refer to action principle, it's just pure math. This is a very mathematically oriented lecture, because I'm just deriving, basically. But I would like to explain what it means to derive. Well, here is what it is. Considering we have these two systems, they are equivalent in a way, because from one we can derive another, and from another derive the first one. So they are equivalent. They're just two different views on the same mechanical movement of system. What does it mean? Well, it means that if I will take a set of coordinates S and a set of coordinates Q, Cartesian and generalized, which are related to these, to each other through these functions. Functions are known. It's like conversion from polar coordinates to Cartesian. It's known functions, formulas if you wish. So this is a formula with parameters q1, q2, qn, and it delivers one particular SI. Another formula would be for another SI, etc. And these are formulas. So these are smooth function, mutually invertible into each other, which means they are describing exactly the same process. So if you consider some mechanical system, it's moving along certain trajectory. What is a trajectory in one system? It will be S1 of t, S2 of t, etc., Sn of t. So these are movement, these are functions now. Coordinate as a function of time. So this is a movement of one system. Okay, let's call it S of t. It's a trajectory. Now, exactly the same trajectory is q of t, where q is related to s, exactly using this type of thing. So, whenever we have the same coordinates, I mean transformable into each other, they describe the same trajectory, physical trajectory. So, physical trajectory is a reality. In some space, let's say we have n-dimensional space. Well, we have three-dimensional space, let's say, and we have n different point masses from which system consists of, which means we have 3n coordinates in any kind of a system. So basically, that's what it is. And these two sets of coordinates describe the same, exactly the same trajectory, physical trajectory, if they are related to these particular transformation functions. So, what we have to actually prove that if this trajectory is a real trajectory of the mechanical system which is moving in some configuration space, and therefore it's supposed to satisfy some Lagrangian Euler-Lagrange equation. So we construct a Lagrangian. Well, let's call it with a suffix c because it's Cartesian, and it's supposed to be kinetic energy in these coordinates minus potential energy. So it would be some function of S1, etc., Sn, S1 derivative, etc., Sn derivative. That's what it is. Now, what I mean about Euler-Lagrange equation in generalized coordinate, it's some kind of a different formula, so I will use suffix g here as a different formula from different coordinates. But the formula expressed in these coordinates, if these coordinates are coordinates of the same trajectory, it's supposed to satisfy the same Euler-Lagrange equation, which means that in this particular case, I know that this is a trajectory, S of t is a trajectory, which means it's supposed to satisfy the Euler-Lagrange equation by d si for each coordinates. It's supposed to be d over dt of dlc by dsi derivative. And with LC, I mean all its arguments. So what I'm claiming right now, that if S is a derivative, is a trajectory, then it satisfies the Euler-Lagrange equation in Cartesian coordinates. We know that. It goes from Newton's second law to Euler-Lagrange equation, this one, in Cartesian coordinates. That had been proven before. So what I'm stating right now, that if the same trajectory is represented by generalized coordinates, then the same equation q and q prime, I will put here, divided by dqi, supposed to be equal to d by dt dlg by dqi prime. So that's basically a theorem which I have to prove, that if S of t and S prime of t satisfy this particular equation, which is Euler-Lagrange in Cartesian coordinates, and the same trajectory is described by functions q, which means it's just description in another generalized coordinate systems, then the equation would absolutely looking the same. So all we have to do is find the kinetic energy in these coordinates and potential energy in these coordinates, construct Lagrangian. So Lagrangian would be Tg minus Ug, kinetic energy in these generalized coordinate minus potential energy. And again, kinetic energy is basically 1/2 of the mass times square of linear speed. I mean, everything is supposed to be exactly like it's supposed to be. And then the equation would be the same. Now, let me wipe out this. This side. All right. So, how do we do it, basically? I mean, what is this? Well, somehow, to prove that this particular equation takes place, I should somehow be able to derive with this equation from this one, right? Okay, but since I know that kinetic energy and potential energy, and therefore Lagrangian, as function of basically any coordinates, if they are transformable into each other, the value itself, the scalar, which is, let's say, kinetic energy in generalized coordinates, which is q1 of t, etc., q n of t, q1 star of t, etc., qn of t. So this is basically some kind of expression of kinetic energy in generalized coordinates. Doesn't matter how I made it. I made it. Okay, now, the value of this at any particular time, whenever the mechanical system is moving along some trajectory, at some particular time it's at a certain point at that particular trajectory. And that point is characterized by all this. And it has certain generalized velocity, obviously, as well. So, some formula, which is this one, delivers the kinetic energy. Now, but the value of this kinetic energy as the value, as a numerical value in some measurement units, whatever the measurement units are, is supposed to be the same no matter what kind of coordinate system I choose. So basically, if this particular trajectory, so if q is q of, well, let's put it qi is qi of s, and si is s capital I of q. If this is the same trajectory, then that should be equal to Tc of c, of S1, etc., Sn, S1 prime, etc., Sn. They are supposed to be equal of time. At any time, at any point on the trajectory where the system is at that time located. So that's a very important quality. Now, same thing with potential energy, and therefore same thing with Lagrangian, which is a difference between potential, between kinetic and potential. So I can use this, but Okay, I can replace Lg of Q to Lc of C. All right, I can replace it. But now I'm talking about differential equation with differentiation by Q in this particular case, which means that I should, now this is a known formula, right? So I have to really express this as a function of Q to be able to differentiate by Q. But I can very easily do it because I know that I can replace S with Q's. So I can say that this is equal to LC, which is known formula for Cartesian Lagrangian, from capital S first of Q. Now Q means Q1, Q2, Q3, etc., capital Sn of Q. Then I have to somehow, I don't know what that actually is, but this is supposed to be derivative. I have to really talk about derivative. So it would be Si of Q, S1, etc., Sn prime of Q. So now this is a function of Q, and I can differentiate it by Q and check if this is really true. Okay, so what's good and what's bad? Well, everything is good except that I don't know what I have S prime as a function. Well, we can derive it from here. That's kind of easy. Let's do it this way. We don't need this anymore. We have to prove that this function satisfies this equation. Well, from here you can see that Si prime is equal to, how to basically differentiate it by time. S prime is derivative by time. Well, this is a function of many arguments, right? Q1, etc., Qn. So whenever there is a function of many arguments, each one is a function of time, and I have to differentiate by time. That's basically sigma dsi of Q1 of t, etc., Qn of t by Qj. I think it would be better if I just skip this by t. It would be a little easier to understand. By j from 1 to n times Qj derivative by time. So this is a chain rule. It's a chain rule for function of multiple arguments to differentiate by internal parameter time in this particular t. Okay, so I know this function. So now I can replace this with sigma from j is equal to 1 to n ds first of q by dqj, etc., sigma dsn by dqj, sigma by j. So my index is 1, 2, 3. The function itself, S function, capital S function, would be indexed. And this index is index of summation. So I have sigma on every level. It's kind of ugly, right? Sorry about that. But now I have completely function which is a Lagrangian of generalized parameters. And now I can check if this function actually satisfies this particular equation. And I'm not going to do it right now, but I did do it in writing. So right now I can refer you to the writing, to notes for this lecture, because it's just pure tedious mass. You have to differentiate by qi, and again it's a chain rule and a couple of more interesting details. One of the interesting details was already discussed in my lecture in the same chapter called Lagrangian Math. And one of the things in Lagrangian Math was ds j by d qi is equal to ds j prime to ds q prime. This is kind of equivalent of the theorem of L'Hopital, whenever we were using the ratio of functions was related to ratio of their derivatives. That's kind of very easy to prove, and the proof is in my lecture called Lagrangian Math Plus. So these are all functions of time, and S and J are related to each other with these type of equations. So it's kind of easy to prove this, and the proof is there. So I use this particular proof. Another thing is, which I'm using whenever I'm trying to check if this differential equation is good for this particular function, is that I know that for Cartesian coordinates, the Euler-Lagrange equation is true, because this is our proposition of the whole theorem. So it will be necessary to use this to substitute something with something using the Lagrangian Euler-Lagrange equation in Cartesian coordinates. And if you are using these two things, basically I will relatively easy, straightforward, but kind of tedious calculations I will derive from this look at this Lagrangian in using Lagrangian in Cartesian coordinates with substitution of functions as a function now of Q, of generalized coordinates. And I'm just checking if this is true, and this is true. So at this particular moment, I just refer you to notes for this lecture. If you want really this tedious calculations to go through, you're welcome to do it. It's all checked, everything is fine. So first I evaluate this thing. So I differentiated the whole thing by one particular qi, get the formula. Then I do this thing, I differentiate it by qi prime, by velocity, and then differentiate it by time, using this thing and using the Euler-Lagrange equation in Cartesian coordinates. So I can substitute something like d by dt dlc of s and s prime by ds prime. I can substitute it with d lc by ds I. Right. So I'm just using this and substituting this to this, and then I get the identity, basically. Oh yes, one more thing. Whenever you're twice differentiating something like this, d2s, let's say j of q, by first you differentiate by qk, qi. So first differentiate by I and then by k. That's the same thing as if you differentiate the same thing in different directions. First q k and then q I. So I can switch. This is also a known fact from functions with multiple arguments. You can just use it without any problems. So again, just go to the notes if you are very curious about the calculation. But the basis, I wanted to explain exactly everything before these tedious calculations, that we are using Lagrangian and Cartesian system and transformation functions from generalized to Cartesian to replace checking of this thing with LG with checking for LC, because LG of q and q prime are equal to this one. And that's the most important key to the whole thing. All right, that's it. Thank you very much, and good luck.